In this question, we've got a situation of having a really thin stick, which is carrying an electric charge. And as a result of that electric charge, it's causing a potential in the space around it. And we've been given an equation here for the potential at a distance r above the center of this stick. So the stick is horizontal. Now, what we want to do is to figure out the potential at that location, but not by using this equation here. We want to figure it out by summing the first 100 terms of the multipole expansion for V. So if we include enough terms in the multipole expansion, well, we should get exactly the same answer that this equation gives here. But it'd be interesting to see, well, just how many terms do we need to include in a multipole expansion to get the same answer as this? And could we sort of reduce the number of terms down to something really small and still get a reasonable approximation? That would be interesting to investigate. So let's do that here. Well, first of all, let's start off by drawing up this stick. Now, I know the stick's supposed to be thin, but just so we can see it on a piece of paper, I'm going to draw it with a bit of thickness. And we want the potential at a point above its center. So let's put that there, call that P. Now, I'm going to put the origin of the coordinate system at the center of the stick, so directly below point P. And if that's the origin, then we can say that the point P is going to have a position vector of r. Now, how we would normally figure out the potential at point P is to divide the stick up into lots and lots of tiny little bits. Let's suppose that we choose one of those tiny little bits to be this thing here. So there is a tiny little bit of stick, and I'm going to say that that tiny little bit of stick has position vector r prime. And let's give this tiny little bit of stick the length dr prime. And since the stick is described as being thin, we can take its thickness to be 0, in which case the length of that tiny little piece is really all there is to know about its size. Okay, so let's write down the multipole expansion. The nth term of it we know is given by this. K divided by r to the power of n plus 1. Then we need to do an integral over r prime to the power of n times the nth order Legendre polynomial of the cosine between r and r prime multiplied by all this. Now, if you remember why this is here, well, this is the charge carried by a tiny little piece of the object whose potential we're trying to calculate. Now, in this case, in this question, we've not been given the volume charge density. So this kind of assumes that we're integrating over a volume. In this case, we've actually been given a line charge density, which is the charge per unit length. So if we're going to chop this stick up into lots of tiny little bits and calculate the potential due to each of them, well, to get the charge on each of those tiny little bits, what we would do is multiply this line charge density here by a tiny little bit of length, i.e. this dr prime here. So in this case, when we integrate over the entire stick, we need to replace this by lambda times dr prime. Okay, so let's just make a note of that. I'll say that lambda is the charge per unit length, not per unit volume. So that means that the charge on a tiny little piece of stick is going to be that lambda multiplied by dr prime. So we're going to replace the volume charge density multiplied by a tiny element of volume with the line charge density multiplied by a tiny little piece of length. And this is the thing that's going to give us the charge of a tiny little piece of stick. One more thing that I'd like to note is that it doesn't really matter where this tiny little element of stick is. Its position vector is always going to be perpendicular to the position vector for point P. So what that means is that the alpha in here is always going to be 90 degrees, and cos of 90 just gives us 0. So we're always going to be wanting to evaluate the Legendre polynomial at 0. So let's just also note that, or say that R prime is always perpendicular to R. So that means that cos alpha is just going to be equal to 0. Now, to sum up the contribution of all the little tiny bits of stick, let's divide up the stick into two parts, the bit to the left of the origin and the bit to the right. So I'm going to say that, well, the total potential, we can write that as being equal to the potential due to the part of the stick to the left of the origin plus the part of the stick to the right. And we can say that, well, both sides of this stick look exactly the same, and they're both the same distance away from point P, so they're both going to make the same contribution to the potential there. So let's say that, well, by symmetry, Vn left is equal to Vn right. So we can write that Vn is just equal to twice the contribution due to the part of the stick on the left. So to figure out what that is, well, we can just go back and use the usual multipole expansion, just making the adjustments that we've noted. So this will be twice k over r to the n plus 1. Then we have an integral over r prime to the n. We're evaluating the Legendre polynomial at 0, and we've already noted that the charge of a tiny little piece of stick is given by this. So we write that as lambda dr prime. Now, to sum up the contributions of all the little bits to the left of the origin, we need to do the integral from 0 up to a, because we know that this part of the stick from the origin over to its left end has a length of a, and of course it's the same on the right. So we're going to sum from 0 to a. Now we've got quite a lot of stuff that can come outside the integral. This is a constant, this is a constant, so we can shove those out the front. And then all we're left to integrate with is just r prime to the power of n. And that's pretty much the easiest integral in the world to do. This will be r prime to the n plus 1. We divide that by n plus 1. And when we just shove those numbers in, we get this. Okay, and we're done. Now we want to evaluate this for the first 100 values of n, so that means basically 0 up to 99, and then add them all up. Now that would be extremely tedious to do by hand. One of the reasons for which is we've got these Legendre polynomials there, and unless you have those stored in your head, they're pretty hard to work out. So let's use Mathematica to actually evaluate this from 0 up to 99, and then add all those terms up. All right, so let's put in all the numbers that we've been given in the question. So we've got the length of the stick is 10 centimeters. We've got the charge density. So to enter the lambda, I've just typed in escape, then type lambda, then press escape again. That's 10 to the power of -6. The A is just half the length. So to put in L divided by 2, I'm just going to press Control and then the backslash. To make the fraction, I'm just going to go L divided by 2. What's next? Oh, we need to give it R. So that's 5.2 centimeters of the center of the stick. And we should also tell it what K is. K is equal to 1 divided by 4 times pi times by epsilon 0. Now it doesn't know what epsilon 0 is yet either, so we better tell it that. Got epsilon 0 is 8.85 times 10 to the negative 12. And I think that's about all it needs. We can now go ahead and give Mathematica this expression for the nth term. So let's put that down here. We've got 2 times k r to the n plus 1. Now we've got the line charge density lambda times by, now to enter in the Legendre polynomial, I want in Legendre P. The first argument tells us the order, which is n. We want to evaluate that at 0. And we're going to multiply that by a to the n plus 1, divide by n plus 1. And that looks about it. Now, of course, we actually want to be summing the first 100 terms. So what we want to do is to evaluate this for all n's between 0 and 99, and then add them all up. To do that, I'm going to enclose this all in a sum. So I'm going to type capital S, U, M, open square bracket, and now put a comma after the thing that we're summing over, put in a curly bracket, type n to tell Mathematica that that's the variable for the summation, and that I want, now I'm going to put in a comma and say that I want to sum that from 0 up to 99, and then do a closed curly bracket and a closed square bracket, and just one closed square bracket will do. And I think that's about it. So let's do a shift enter on that, and we end up with 15,356.3 volts. All right, so this is our approximate value of the potential based on the multipole expansion. Let's now try using this equation here to see how close this value is to the exact value. So let's say that the exact, I'm going to put this equation here in now. So really we've just got k times lambda, and we want to multiply that by the log. So in Mathematica, ln is actually written as log. So that's one thing you need to remember. Then we've got open square bracket, and now we need to put in this nasty looking fraction. To make a square root sign, I'm going to press Control and then 2. And there we go. And in the denominator, we have minus a plus square root of all that stuff. And then we need to close off the square brackets. And I think that's about it. So let's do a shift enter on that. I've got something wrong here. I've put in a double plus sign for some reason. Don't know why I would put in a double plus sign, so let's get rid of one of those. And shift enter again. All right, so that's given us 15,356.5. So basically the two potentials are out, well, our approximation is out by 0.2.